Okay, so we are going to move on to working on 5.2, kind of wrapping it up. So we're going to get a theorem, and this is going to be what happens if we integrate over a constant. So we're going to say for any constant, C, we get the following thing. The integral from a up to b of the constant dx is going to be c times b minus a. So it's the constant multiplied by the length of the integral. And why this kind of works is if we have a graph and we have a constant, let's say our constant's like 7, so we have a horizontal line here at 7, and we want to know what's the area under the curve from 1 up to 3 of 7. Well, that'll kind of make a area that you're trying to talk about. The height here will be 7, and the length here will be 3 minus 1, which is 2. So length times width would equal area. So that's basically what we're seeing here. C is the height, and b minus a is the length of the interval, and that holds for constants. We also get linearity with our definite integral operator. So we would have the integral of a to b of f of x plus g of x dx. That will equal the integral from a up to b of f of x dx plus the integral from a up to b of g of x dx. So linearity basically says you can split the integral of the whole part. You can split it up to talking about the integral of the individual pieces. If we integrate over a constant, so we say integral a to b of c f of x dx, that will equal c times the integral of a up to b of f of x dx. So you're able to pull the constant out front of the integral. So next what they're going to do, we're going to do a quick example where they're going to give us another formula, and we're going to kind of put some of this stuff together to solve it. So for this example 3 here from the book, they want us to calculate what's the integral of 0 up to 3 of 2x squared minus 5 dx. And they give us the formula that the integral from 0 up to b of x squared dx is going to equal 1/3 b cubed. They write it as b cubed over 3, but I'm going to write it this way. So they give us this extra formula and say, use that formula in order to do this. So we're going to have to use linearity, and we're going to have to split the integral across the individual pieces, and we're going to push the constant 2 out front of the first integral. So we're going to say by linearity, we can, so we're going to use linearity. We're going to be able to talk about the integral of the 2 individual terms. And I'm going to be able to push the 2 out front of the integral in the first term. So when I get this done, this part right here, I'm going to box it in for just a second. This part right here, we can evaluate using that expression right there. So we'll say, all right, this is going to be 2 times integral from 0 up to b. b is acting as 3. This will equal 1/3 times 3 cubed. So that will be 1/3 times 3 cubed. Minus the integral from 0 up to 3 of 5. This is the integral of 0 up to 3 of a constant. That's going to be this one right here. 5 is our constant, and we'll put the upper limit of the integral minus the lower limit of the integral. So we'll get this as 5 times upper limit of the integral 3 minus lower limit of the integral, which is 0. So now we just have to kind of algebraically simplify this down. 3 cubes, 27. So we have 27 divided by 3, which is 9. So we get 2 times 9 from that first term minus 5 times 3 minus 0 is 3. So this is, let's see here, that's going to be 18 minus 15, which is going to total up to 3. And that'll be our answer for that one. So we use linearity to split up the integral into the individual pieces. When we pushed the 2 out front, we were able to get our integral here was in a format we could use the equation they gave us. And then for the rest of it, for this part, we used the constant equation, and then we were able to simplify stuff down. So now we're going to get a whole bunch of other little interesting things, I guess. So we have a definition. This has to do with reversing limits of integration. And for this, we need a to be less than b. Then we say if you have the integral from b up to a of f of x dx, so you have your integration like this, if you want to flip that integration over, so whenever you flip the limits of an integration over, you switch the sign out here. So we have integral from b up to a. I want to switch the limits over and make it a up to b. When I do that, that creates a negative out front. So that's one nice little equation we want to keep track of. They give us another that says if you have the integral from a up to a of f of x dx, that's actually 0, which kind of makes sense because the integral is related to, it's the definite integral is assigned area under the curve. So if your starting and stopping place is the same number, there's no area mapped out by that. So this one kind of makes sense from a kind of geometric idea. Then we have the integral from 0 up to b of x dx is going to be 1/2 b squared. So we got these nice little groups of equations. They give us one more theorem. So, sorry, the definition was only this first equation here. These other two are just some miscellaneous little fun equations we kind of get now. So down here we get a theorem. And this one is additivity of adjacent intervals. So we're going to let a be less than or equal to b, be less than or equal to c, and we assume f of x is integrable. Then if we have the integral from a up to c of f, a up to c of f of x dx, we could split this up into, instead of a up to c, we could split this up into the integral from a up to b, and then the integral from b up to c. So we could say this is going to equal the integral from a up to b added to the integral b up to c. It kind of makes sense. If b is between a and c, then the total signed area under the curve from a up to c, it kind of makes sense. You could make the signed area from a up to b, find the signed area from b up to c, and then if you add those two signed areas together, that would equal the total signed area. So that maybe seems like it's kind of a reasonable thing. It shouldn't kind of make sense, I guess. So we're going to do a quick example of this, and then we're going to move on over to our last theorem and our last idea, and then that'll wrap up the section. So here we want to calculate, for this is example 5, we want to calculate integral of 4 up to 7 of x squared dx. Now, the only x squared equation we've had so far has been this one right here, but unfortunately this one starts at 0. It doesn't start at 4. So what we're going to do is we're going to say, well, let's talk about the integral 0 to 7 so we could use that equation. I could break that integral 0 to 7 up into the integral 0 to 4 x squared dx, and then the rest of it would be 4 up to 7 x squared dx. This is the integral I'm Sorry, these would be added together. This is the integral I want solved for. So what I'm going to do is take this integral here. I'm going to push it back across the equal sign. It was a positive integral here, so it's going to turn up as negative of that integral when we push it across the equal sign. And now we have an expression for what we're trying to solve for, the integral of 4 up to 7 of x squared dx. Both of these integrals start at 0. They stop at a stopping number. If we look back to that equation, it says if you start at 0 and go up to a stopping number of x squared dx, that is 1/3 times your stopping number squared. So it's 1/3 times the upper limit squared. So this will be 1/3 times the upper limit, which is 7. Sorry, was it squared or cubed? I think it was cubed. I think I was saying squared. Yeah, it's cubed. 1/3 times 7 cubed minus the integral of 0. Oops, no, just kidding. We can evaluate this. This also starts at 0, goes to an upper limit of x squared. So it will be 1/3 times its upper limit cubed. That will equal the integral that we want. And so we'll just, I guess, toss those into the calculator here. We'll get 1/3 times 7 cubed minus 1/3 times 4 cubed. This is going to equal 93. So 93 equals the integral from 4 up to 7 of x squared dx. That is the number we wanted. Later on in section 5.3, we'll learn a quicker way where we can just directly get at this integration without having to start the integral at 0 each time. We'll be able to start the integral at 4 up to 7. So we'll get an equation in 5.3 that'll let us handle this directly instead of having to get the integral from 0 up to 7. But for now, this works. Okay, so last theorem, and then we'll talk about a result from that, or a theorem and example, then a result, and then we'll be done with the section. So last theorem says, this is comparison theorem. So this says if f and g are integrable functions, and g of x, so the g function, is less than or equal to the f of x function for x in a region a to b, then the integral over that region of g of x is less than or equal to the integral over the region of f of x. So the integral over the region of g of x is less than or equal to the integral over the region of f of x. And to kind of see this, suppose we had a g of x function. Let's draw it here. So let's say we had a g of x function that was like that, and we had a f of x function that was taller than the g of x function. And let's say we're looking at the interval from a up to b, and let's say g of x is this shorter function, and f of x is this taller function. So f of x is greater than g of x over the region a to b, because f of x is always larger y values than g of x for everyone in the region. So if we kind of look at a to b and we say, okay, what area, because the integral from a to b of g of x dx will be the signed area under the curve. So we say, what area does g of x map out? Well, g of x maps out this little area right here. That's what the integral of a to b of g of x dx would represent. It would represent this little bit of area here. Say, well, what about the integral from a to b of f of x dx? Well, since f of x is higher, it will map out all the way up to here. And we can see that since it's a taller function, it's going to have a map out more area beneath its curve. And so this kind of justifies, as long as whoever the taller function is, whoever's the bigger function over the interval, when you say how much area is under their curve, they'll have more area than the smaller one. And that's basically what the comparison theorem says. So for an example of this, this is going to be example 6. We want to prove that the integral of 1 up to 4 of 1 over x squared dx is not equal. It's less than or equal to the integral of 1 up to 4 of x dx. So basically what we're going to have to do is eventually, so our goal is to show 1 over x squared is less than or equal to 1 over x over the interval 1 up to 4. So this is, if we can get to this, then we can use the comparison theorem to show that it holds for the integrals. So we're going to start out, as long as you're, for x in 1 to 4, the following inequalities that we put down are going to be true. Well, if x is in 1 to 4, then x is always bigger than or equal to 1. Because x, if you're in the interval 1 to 4, the smallest, if you're in that interval, the smallest number you can be is 1, the biggest number you can be is 4, and all the numbers from 1 up to 4 are bigger than 1, or if you're 1 itself, you're equal to 1. We're going to multiply both those by x. So when I multiply these by x, I get that. So we get x is less than or equal to x squared. Should be a little careful. X is in 1 to 4, so it's a positive number. So when I multiply through by a positive number, I don't have to switch the inequality directions because the x's are in 1 to 4, and all of this, these are all positive numbers. So inequality direction doesn't flip from that. Okay, so I get my inequality like that. Next, I'm going to raise both of them to the negative first power. So when I do that, when I raise these to negative first power, the inequality direction flips. And so what we currently have is 1 over x is greater than or equal to 1 over x squared, which that was what we were wanting to show, 1 over x greater than or equal to 1 over x squared. So we got that. So then by the comparison theorem, we get the integral of 1 up to 4 of 1 over x dx is greater than or equal to the integral of 1 up to 4 of 1 over x squared dx. And I believe that's what we were trying to show. Yes, so we got that one. Whoops, this one should have been 1 over x. So we have integral 1 up to 4 of 1 over x is greater than or equal to integral from 1 up to 4 of 1 over x squared. That's what we're trying to show. So we got it here, and that wraps that example up. Okay, the last bit we want to talk about is if there is some m value here, and that m value is less than or equal to some f of x value, which is less than or equal to some capital M value for x in some interval a up to b. We want to kind of make a note of how would stuff relate there. M and capital M are constants. So let's say we had a graph here, and let's say that m is down here, so this is my constant m down there, and let's say capital M is way up here, so this is my capital M, and my function f of x is supposed to be in between those, so let's just say the function f of x is some little curved line that's going in between. Okay, we're looking over intervals a up to b of all three of these. So what we get is, if we look at the area under the curve of m, since m is a constant, that will be the area under the curve of m, I guess we'll just write it off to the side. The area here would be m times the upper limit b minus the lower limit a. So m sets a height, and then b minus a sets the width. Since it's like a rectangle, you get the height times the width, and we get that expression. We can see that the area under the curve of f, it is bigger, it includes more area than the m, the area under the curve of just m. So it's includes all of m, and then since the f of x can be larger values, it includes some region in between. The area under f of x would be the integral from a up to b of f of x dx. And finally, if we look at the area under the curve of capital M, since capital M is above everybody, its area will encompass everyone else's area, and this will have the most area. And its area will be, since M is a constant, it will be capital M times the interval length b minus a. So kind of based on what we have there, we could see that we can generate this equation that if M is less than or equal to f of x is less than or equal to capital M for x in a minus b, or x in a up to b, then the area under the curve of M, which is M of b minus a, that will be less than or equal to the area, the signed area under the curve of f of x dx, which will be less than or equal to the signed area under the curve by mapped out by capital M. And so we can kind of see with this little picture here. Area under the curve of M is just this little part down here. The area under the curve of f of x is kind of this medium, slightly taller. And the area under the curve of capital M is all the way from down to top, so that's the biggest area. And so we can kind of see that these would, this inequality is true, and kind of verify it, or this area argument kind of might convince us that this is working the way we want it to. So that's going to wrap it up for section 5.2. We're going to stop there, and we'll say it's good enough for that.